Alright, so let's start the first video. In this example, we have a simple root locus. It's the first thing that we have to do is to write it in the standard root locus form, and that is write it in the characteristic equation. So we say CE is 1 plus K G of S. Okay, so this is the standard form that you have to write it to make things easier. So our G of S is this, right? Except the K part, okay? So what we're gonna write is to 1 plus, so let's call it T of S, okay? So actually let's just call it characteristic equation of S. 1 plus K and then the actual equation. So that's it, okay? And now we have to find, the first step that we had to do was to find the poles and zeros. So let's call n poles, okay? And we have two poles, one at 0, one at -1, okay? 0, -1, so 0 and -1. Do we have any zeros? So in case you're new in these stuff, whatever is on top is called zeros, whatever is in bottom is called poles, okay? Why are they called poles and zeros? Because let's say you have this equation, okay? Let's say you have s plus 1 and then s minus 1, okay? Let's say you have this equation. If you draw, like not draw, but like if you say s equals -1, right? Okay, I'm gonna s equals -1. If we say s equals -1, what happens? We have -1 plus 1, right? And then -1, -1, which is 0 over -2. So, and then 0 divided by a number is just 0. So by 0, we mean what value should we select that makes the whole equation equal 0, okay? So that's why we call it 0. And for the pole, it's just the inverse, okay? So if you say s is 1, it's just going to be 2 over 0, and 2 over 0 is just infinity, okay? So that's why we call it pole and zeros. So the top part is called zeros, the bottom part is called poles, okay? So just remember that, because I won't be repeating this since you already know, and we're just going to go ahead with it. So next thing is we have to determine the zeros, and I'm going to call the zeros M, okay? You can call it X, Y, Z, W, I don't know, whatever, right? It's just a symbol, doesn't matter. Do we have any zeros? No, we do have no zeros, so it's just, sorry, not 0, but we have no zeros, okay? So it's nothing. And how many poles do we have? We have 2 in total, right? We have a 0 and a -1. And how many zeros we have in total? We have nothing, so it's just a 0. Now, the next step is to find the asymptotes. Okay, so I think it's better if I write it in this order so that you can see and follow through. So the first step, find the poles, zeros, number of asymptotes. So we found the pole, we found the zeros, we have to find the number of asymptotes. How do we find the number of asymptotes? It's just easy, okay? So we're just going to call it number of asymptote, ASI, and then n minus m. That's the formula. How many poles you have, subtract how many zeros you have. That gives you your number of asymptotes. In our case, it's just 2, okay? So 2 minus 0 equals 2. That's it. So we have 2 asymptotes. Now we know how many asymptotes we have, so that's done. So the first step is done. Next step, we have to find the angles of these asymptotes. So there is a formula for that, okay? And the formula is, okay, so this is a formula. And we have 2q plus 1 over n minus m times 180, where q just represents the number of the asymptotes that you have, and they always start from 0 until you reach the number of asymptotes. So in our case, q is just n minus m minus 1. That's the formula for q, okay? And which is what? n is 2, 0 minus 1, 1, okay? So this means that q goes from 0 and then q equals 1. That's it. We only have to find this for these two, okay? So now let's see. First angle is 2, 0 plus 1 over n minus m is just 2 times 180 equals 90. 2 times 0, 0, 1 divided by 2 and then times 180 gives you 90 degrees. And then for second asymptote angle, 1 plus 1 over 2 times 180. And 270. And if we draw this here, okay, this is 190, 180, 270, which is just another way of saying minus 90. So we write minus 90, okay? That's it, right? 90 minus 90, okay? So we did the second step. So second step is also done. First step is done. Now we have to find the centroid. Let's call centroid C, okay? So step 3, centroid C equals, the centroid is the sum of poles minus sum of zeros divided by n minus m. By sum of poles we mean, so it's going to be 0 minus 1, right, minus 0, 2 minus 0. So this is going to give me a value of minus 1 over 2. So it means that we have the centroid as negative 0.5, okay? And this centroid is where you're going to draw these two angles, okay? So these angles for asymptote always go on the centroid. So that's it, okay? 3 steps done, easy. Now we have to find the break-in, breakaway points. This is where you need some, you have to remember your calculus class, okay? So I'm gonna call this just B of S, okay? Because G of S has the K, B of S doesn't have the K, so I'm just gonna call it B of S. So the formula for to find the break-in, breakaway point is just we have to find a derivative. Apologies. So we just have to find the derivative of this term with respect to S. That's it, okay? That's all you have to do in order to get the breakaway and breakaway points. And this is the same for, even if you have a very complex equation, this is the basic idea that you have to apply, okay? So if you take the derivative of B of S with respect to S, we have a U over V, okay? Where our U is 1, our V is S squared plus S, and then our du is 0, our dv is 2s plus 1, okay? Now, how do you find the derivative of such an equation? It's just u over v equals u prime v minus u v prime over v squared, okay? So that's the formula to find the derivative of such equations. And so we already know our u prime v prime. Now we're just going to write it down, okay? So u prime is 0, 0 times something is 0, and then minus u is 1, v prime is 2s minus 1, okay, because minus, right, becomes minus, over v squared is square plus s equals to 0. So if we try to solve for s, this term goes here, multiplies by 0, becomes 0. So we are only left with a negative 2s, negative 1, and if we just, change the signs, it's just going to become 2s plus 1 equals 0, and s equals negative 1 over 2, negative 0.5. So this is our breakaway points. For such systems, these 2 points are always the same as the centroid, but it's going to be different for when we have another examples with higher degree of polynomials. That's when we're going to have a bit more math to do. Okay, now, so this point is also done. Now we have to determine whether it crosses imaginary axis. Well, let's look. Okay, it's just a simple s squared plus s with a asymptote of negative 90 plus 90, so it doesn't cross the imaginary axis. Okay, if you try to solve for imaginary axis, the formula is to take the characteristic equation which we wrote earlier, which is just 1 plus k, right, is plus 1 equals 0, and this is going to be s squared plus s plus k equals 0. So next step, we have to find the Routh-Horowitz method. You don't have to know this for this case, okay? Because I will explain it in the next example that we actually have to use it. But even if you use it in this case, it's just gonna give you a imaginary k, which is just not right, yeah? Because k doesn't cross so the imaginary axis, so it shouldn't have an imaginary component. Okay, so this step is not eligible for this example specifically, okay? For this, for this. Departure, arrival angle, do we have any? No. How do we know? Because our equation is this, right? It doesn't have a complex zero, it doesn't have a complex pole, so it doesn't have an it doesn't have a departure or arrival angle. Now we have to draw the root locus, so we're just gonna draw this, okay? I'm gonna draw this. This is the real axis, okay? Real axis. This is the imaginary axis, and let's locate our points. So we have a pole at 0, we have a pole at -2, so -1, -2, okay? So 0, -2. So we have a 0, we have a -2, we only have these two poles. We have a centroid, right? We have a centroid, where was it? Here, at -0.5. So we have a centroid right here, which is also the location of the breakaway breakpoints. So we have the centroid at -0.5, and the angles are at -90 and +90. So the angles are just that, okay? 90, -90. And now when we have to draw the locus, so this goes up to here and then goes upwards, okay? And this goes up to here and then goes downwards. And for root locus, it's important that you draw the arrow, okay? So like this, let me draw a better one for the zeros. Okay, so why is it not working? Okay. All right, so like this, okay? And like this. Sorry, not like that, I mean like this. Because these just go to infinity. They go as long as, it's basically infinity, okay? Both ways. So as you can see, right, this orange locus starts from the pole, right, goes to the left, and then goes upward to infinity. And this other locus starts from -2, goes up to the breakpoint, and then goes down to infinity, okay? Down to -infinity. So this is it. This is the root locus for a very simple case.